Thank you. It's delightful to be here. So today I'm going to show you how magnetic reconnection can populate a spectrum of non-thermal particles. So instead of giving you a specific astrophysical motivation, I'm going to state more generally that in astrophysics there are many stores of energy, and that non-thermal particles are one of those and are a very well-connected source of energy. And so it stands to reason that particle injection, which is the generic precursor to non-thermal particles, understanding that better is going to have rippling implications across the sort of energetic landscape. And in the context of magnetic reconnection, we've known for a decade that power law distributions are producible. And in general, such power laws can be characterized by three parameters: the power law index, the upper bound, the cutoff, and the lower bound, the injection energy. And those parameters can be seen on the spectrum, where I've denoted the magnetic energy as sigma equals 32 per particle rest energy, otherwise called the cold upstream magnetization parameter. And the acceleration of particles within the power law beyond this injection energy is likely dominated by a continual Fermi process. But what has been less understood is how particles enter the power law from thermal upstream. In other words, how the power laws are populated. Oh, whoops, sorry. So it's this populating of the power law which I term injection. In other words, a particle is injected if it satisfies a certain injection criterion. That criterion, for example, can be a particle which surpasses a characteristic energy scale. Maybe one might call this the injection energy, and an injection mechanism is a physical process which accelerates a pre-injected particle to advance it towards satisfying that criterion. In other words, an injection mechanism injects particles. So with those definitions, the injection problem can be recast to just two questions. What is and what sets the injection criterion, and what mechanisms accelerate particles to satisfy this criterion? So it is around these questions that my talk will be structured. So first, what sets the injection energy and what is the injection energy? So these are questions of model and measurement. So let's begin actually with what sets the injection energy. So to answer this question, we must first ask, what counts as an injected particle? Well, these are particles which have unlocked the acceleration mechanism that operates in the power law of the non-thermal particle distribution. Well then, how might a particle unlock such a mechanism? Well, it depends on what that mechanism is. And in magnetic reconnection, very plausibly, it is stochastic acceleration. But then how does a particle begin to participate in that? Well, so our position, or what we suspect, is that particles in elementary current layers must feel both sides of that layer. And so one way of achieving that is to have a gyro radius which exceeds the half thickness of the current sheet. And that current sheet thickness is approximately the electron skin depth after relativistic corrections. So satisfying this criterion allows particles to engage in a Fermi process. This is quite similar to a poster outside by Naveen, in which there's Kelvin-Helmholtz and drift kink instability occurring at the same time. And it is a similar criterion for power law formation. So how does this translate to an injection energy? So we must remember that the layer thickness is determined by the skin depth in the layer, which in general may be quite different from the upstream skin depth. So we must account for the increased plasma temperature in that layer. In other words, we have to model this factor of gamma, which is the average Lorentz factor of particles in the layer. So let's assume it takes the following form, where gamma up is the upstream, the average Lorentz factor of upstream particles. And if the upstream particle distribution is thermal, then that is approximately the average energy of a Maxwell-Eutner distribution of temperature theta. And this W is the typical work done to particles in the current sheet, which scales linearly with sigma. And from simple energetic arguments, one can constrain this prefactor to be no larger than 1/8, possibly much smaller than 1/8. So algebra from here yields an injection energy, which is a function of three dimensionless quantities. And what's interesting about this formula is that there are or rather two subregimes of reconnection are embedded within it. So there's a regime in which sigma h is less than k to the minus 1, but still exceeding 1. And this we can term the thermally dominated regime because the current sheet temperature is actually inherited from the upstream. And in such a case, when the upstream is cold, then the injection energy scales actually like square root of sigma. On the other hand, in the magnetically dominated regime, the injection energy scales like sigma, and the temperature of the current sheet is actually set by the self-consistent heating that occurs, or the energization that occurs from magnetic reconnection. So let's test this. We now have a model, and we can straightforwardly test it. So to investigate this, we run 2D and 3D kinetic pick simulations using the Zeltron code. So this is a collisionless paraplasma, which we initialize as a force-free current sheet, and we let it reconnect spontaneously. And in this, we track 1 million tracer particles selected uniformly and randomly at the start, and of these 1 million particles, roughly 300,000 end up injected. So our parameters are as follows. We scan 5 values of sigma in 3D, and we scan 8 values in 2D. We use a weak but finite guide field of 0.3, and we use a relativistically lukewarm upstream temperature, 0.3. So to find the injection energy, we first measure the power law index, which are new. So we have a new fitting procedure to do this. You can check it out in our just recently submitted paper from yesterday. And so we can now do this within about 3% accuracy. So doing so means that we would, so after measuring this power law index, we can march backwards in energy and see when the local slope of the spectrum deviates from the measured power law slope by a fixed amount, like 0.1. And then we define that as the injection energy. So here's what it looks like for 3D simulations. So these black lines are the fits. They extend from the injection energy at their lower bound to the cutoff at their upper bound, and they adhere very well to the spectrum. So this just gives you a sense of how precise the measurements have gotten. So let's plot this against sigma. Here are our measurements. Let's see how our model does. So our model seems to fit the 2D data quite well, fitting just below every data point. But this critically requires us to be in the thermally dominated regime. So this suggests that K is actually very small, much smaller than one would sort of maybe naively expect. And so one possibility for why the data points do sit just slightly above the curve is that it's not one skin depth, that the elementary current sheets are thick, but maybe 1.5 or 2 or just a little bit thicker than one skin depth. By contrast, the often assumed sigma over 4 model for the injection energy seems to not account for how low it is in our measurements. In 3D, on the other hand, neither model seems to agree quite. We need more measurements, I think, at higher sigma, which are quite expensive to acquire. And we probably also need more sophisticated modeling, which accounts for the complicated structure of the current sheets that we have. Okay, that brings us to the second question. What mechanisms are accelerating particles to the injection energy? So here's a cartoon that shows magnetic field geometry during the reconnection of a collisionless paraplasma. So in this cartoon, 3 mechanisms are clear. First, we have particles that are accelerated directly by the out-of-plane electric field in the reconnection diffusion region and are subsequently diffused or advected downstream. How much work is imparted to these particles, though? It is how many cyclotron periods the particle remain there times 0.1, the reconnection rate. So a finite guide magnetic field might actually prolong the duration over which a particle remains in this X point, thereby increasing energy gain. So this has been shown in several studies by now. Second, we have a single Fermi reflection off of a reconnection outflow. So if you treat the kick as a 1D particle collision, you can calculate the amount of work done to this particle. And we find that one finds that it scales linearly with sigma, but only if the guide field is much smaller sorry, only if the guide field is small compared to sigma to the minus 1/2. So otherwise, this mechanism is suppressed quite dramatically, and you'll have something like independent of sigma for the work done. And that has also been confirmed by several studies, injection studies. Third, we have pickup acceleration, in which a particle crosses over the separatrix and is swept up in a relativistic outflow, whose speed the particle is accelerated to match. So this translates to this energization. While this mechanism does strictly less work than the Fermi process, it can nevertheless inject particles when sigma is of order unity, especially if we embrace the injection criterion to be a gyroradius, because this mechanism preferentially accelerates particles in the perpendicular direction. Okay, so we have these three mechanisms, but how are we going to quantify their contributions? Seems complicated. But luckily, each mechanism imparts a different experience to the incoming particles, meaning that different electric fields accelerate them and they gain different components of momentum. So in fact, we can use these differences to identify and in fact characterize each mechanism. So in direct acceleration, the non-ideal electric field is accelerating, and if there's a sufficient guide field, W parallel can represent it very well. And of course, these particles gain parallel momentum. For the other mechanisms, it's the motional or ideal MHD electric field that accelerates. But with Fermi kicks, it's parallel momentum which is gained, thanks to the second adiabatic invariant, bounce invariant conservation. Whereas in pickup acceleration, it's the magnetic moment conservation which is violated that allows it to makes it gain perpendicular momentum. And this is momenta in the E cross B drift frame, importantly. So our characterization scheme is to evaluate these quantities at the first time step at which a particle exceeds the injection energy. So notice there's a fourth possibility, namely if you have W parallel, W perp less than W parallel, and P perp greater than P parallel, this fourth one. And so we can include that to test the robustness. You know, I don't know what mechanism this would correspond to. You can think about that. But so our process is to iterate over hundreds of thousands of tracer particles and to check these conditions as we go, and then assigning every tracer particle an injection time and an injection mechanism. And so I should mention also that this procedure is sort of has a great advantage, which is that it's coordinate free, and it can be implemented in any number of dimensions or any geometry without any difficulties. So with this scheme, we can construct what I call injection shares. An injection share of a mechanism is its time-dependent percentage contribution to the total injected particle population at that time step. So here are the injection shares at sigma equals 16. We see that direct acceleration in solid lines dominates for the first light crossing or so after reconnection, but is then taken over by Fermi kicks. And then Fermi dominates in this case of 0.3 guide field. The pickup process in dotted lines remains subdominant, however. Now let's see what happens when we vary sigma. We see that the Fermi share increases at the expense of the pickup share, and the pickup share is vanishing with increasing sigma. So this trend implies that the Fermi and direct shares will remain competitive as sigma increases, provided the guide field is sufficiently weak for Fermi to remain competitive. So this is actually consistent with the formulae that we mentioned before. The work done by these mechanisms, Fermi and direct, are both proportional to sigma, whereas the work done by pickup is proportional to square root sigma. So this is exactly what you would expect. I should say the last point, which is that these mechanisms activate in a particular order. I don't have much time left, but I can show a movie here of the corresponding the injection shares as they go on with time and the plasma as it evolves. So as direct acceleration is activated, we see the next point collapses. As Fermi is activated, we find that the outflow has grown, and as pickup activates, it has widened. And so there is correspondence between the cartoons that I showed earlier, the injection shares, and the movie below. So it's a consistent activation sequence. Now, I have another couple slides, but I'm out of time. So, yes. Thank you.
Oh, yeah, okay. Thanks. So, okay, repeating, I was wondering about the last movie you showed then. Can you go back to that? Yes. So, okay. You're showing here your reconnection simulation from the beginning, I'm assuming, right?
Yeah, from onset.
Right. So if I think about this in a realistic scenario, you will always have a current sheet, let's say, in the state that you're now showing as the very last couple of seconds of this movie, basically, or actually maybe even later than that. So what does that tell us in terms of the mechanism of injection? I mean, that basically we should ignore everything we see until, I don't know, 0.8 to 0.9 of this time on the x-axis, and then think that what injects particles in, let's say, steady state reconnection is only, I don't know, the shares of injection importances are the ones that I see at the very end of your movie, basically?
Yes, so this is a good question. So unlike the previous injection shares plot, which was normalized to the total number of injected particles, like the vertical axis was a percentage, so they each added to 100%. This is absolute number of tracer particles injected. So the absolute number, of course, increases monotonically, like a particle can't be, or at least we're not considering to be uninjected. And so, you know, this sort of, it is a dynamic picture. So early on, direct acceleration composes the vast majority. In fact, for the first quarter light crossings, it's like 100% of the particles are from direct acceleration. But then as time goes on, you know, and things develop, that dominance shifts. I don't know if that answers your question.
Sorry, I'm going to stop. So I guess the real question would be, you know, okay, I understand that this is the dynamical picture, but then let's consider the state of steady state reconnection where you know nothing about what happened in the very beginning of the system, where you were creating the different sheet, or you were going to steady state. What is that inject particles then? Like, what is the inject particles at steady state reconnection?
This is a cumulative distribution, so it still adds to the distribution. You know, if a particle happens to be injected like one light crossing after onset, it still contributes just as well as if it was injected at onset or sooner thereafter. We can talk after.
Thank you, Fabio. Anatoly and then Lorenzo.
Yeah, so some of the criteria for determining which mechanism you're using, they all rely on having definition of perpendicular and parallel.
Yeah.
Are you running into a problem in the middle of the current sheet where B goes through 0?
So this is exactly
what do you do there?
This is why we selected a guide field of 0.3.
So all right. So none of this. All right.
To avoid this problem, but actually selecting a guide field of 0 would be quite interesting to test this sort of proposition that like the particles have to feel both sides of the layer. So, but we'd have to think about it, how to do that.
I have a question on the like the choice of the initial temperature, right? Because it feels a little bit maybe that you're sort of like complicating your life by having a plasma that is already trans-relativistic in the upstream. If you just want the energization to be a result of the dissipation. So I was just wondering whether you have a sense of, especially given that you said like the 2D picture seems consistent with just like the thermal dominating the dissipative part, whether things would change if you were to pick a cold upstream, or why you have chosen not to pick a cold upstream.
Well, well, with 0.3, the gamma thermal is about 1.7. So, I mean, I guess it brings everything down by a factor of like 1.7, but it doesn't really add too many complications because, I mean, we're still very solidly within, like we have captured the, you know, we've captured both regimes. Like near, so it's sort of hard to, I did not mention this, but it's, you know, looking at the injection energies as they scale with sigma here, early on, it's sort of, or sorry, at lower sigma, the growth is a bit slower. And then comparing between 48 and 96 in 2D, it actually seems to grow just a little bit more, like closer to linear. So I think we do capture the transition. And if we like looked at a colder value, maybe we wouldn't have. But yeah.
Okay. Any other questions? Okay. Well, in that case,
Okay, another question. Okay.
like a rephrasing maybe of Fabio's question, which is that in some sense, maybe the one interesting diagnostic would be what is the injection mechanism when most of the particles are being injected.
Oh, okay.
Right?
So like like if you took a time derivative.
Exactly.
Yes.
Or, I mean, the other way I would phrase this is like if you're really in a steady state, which means that you need to have outflow boundaries. At that point, you can make this measurement, and at that point, that measurement would be time independent, most likely.
That's right. So there is a point where the injection due to the Fermi kicks just, it grows from 0 to overtaking direct acceleration. So, I would suppose that there would be sort of a dramatic increase there. But I have not looked at that. It would be very interesting to look at.
Okay, one last question from Leah. Oh.
Thanks, Omar. So I was wondering if you could speculate on your speculation a little bit here. So you're speculating that this discrepancy between the 3D and the model is due to sheets disrupting at greater thickness in 3D.
Yeah.
I mean, I would think that like the plasmoids aren't tubes, kind of like what we talked. Can you guess as to why that leads to a higher injection energy?
Yeah. So this would just come directly from the model. So the injection energy comes from this delta over 2 being approximately dE rel over 2. So if instead of dE rel over 2 is like 3 dE rel over 2, this would triple the injection energy that you would get in the end. So it would just from that, that's how like the injection energies would be higher if the layer couldn't support, like sort of disrupted at that greater thickness. And so the speculation for that is just because in 3D that you have other instabilities that are ongoing, but I think the modeling does have to be more sophisticated if we really want to understand it, because it's just a speculation.